Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Welcome to this 79th Australian Water School webinar brought to you by IceWarm. We're so glad you could join us today to discuss this critical issue of Are Your Pumps About to Fail, presented by Dr. Robert Keller. My name's Trevor Pillar. I'm the National Partnerships Manager here at IceWarm and the webinar chair at the Australian Water School. Well, look at that map. That is a great spread of attendees. It's obviously a key topic, and we're going to have a really good discussion. I'm absolutely sure of that. There's a lot of training coming up in the next 2 months and a lot more next year, but here's the next two or 3 months worth. I won't go into each one. There's just so much happening. We'd encourage you to go to our website, Twitter, LinkedIn and Facebook, and get all the details about these upcoming events. For today, the agenda is a 60-minute webinar, presentation and Q&A included. We'll be recording it and sending that link to you, and the recording will be available on the website and YouTube channel free of charge, of course, as always. Well, let's get right into this. We welcome today Rob. If you'd like to switch your camera on, if you're there, that'd be great. Dr. Robert Keller from Monash University has over 40 years experience in civil engineering hydraulics, currently a consulting engineer, and conducted many technical courses across Australia and Southeast Asia for practicing engineers. So great to welcome you today, Bob, from sunny south of France, or wherever it is that you are presenting from today.
I wish. No, I'm in Melbourne.
Sunny Melbourne, or drizzly Melbourne, or
sunny Melbourne.
It's
well,
great.
It is actually a nice day today, so I'm quite happy about that.
Lovely you could join us. It's going to be an interesting time. I can't help seeing the picture on your wall and wondering what it might be of. From some time back, it looks to me. That's better. Tents.
Yeah, tents. That's my grandfather with the theodolite. He was an engineer, and
right.
And that photograph was taken while he was in charge of the construction of the main trunk railway line in the North Island of New Zealand. Late
1800s, early 1900s, that far back?
Around about early 1800s.
Yep. Oh, that's fantastic. That's a really good photo. I think we're going to just hand right over to you, Bob, and get this thing underway. Everyone, be sure to write in on the Q&A line any comments, any questions, things you'd like discussed. Get them in early, get them in often, and we'll deal with them mostly at the end of the talk. But if you've got some questions as Bob goes through, we can also do that. So without any further, I'll hand over to you, Bob. All yours.
Okay, yep. Are you about to fail?
Yep.
Now, look, my own interest in this topic goes back perhaps 25 or nearly 30 years. And, I got involved in a couple of pump stations where they had been built. Then during operation, they showed some rather unfortunate tendencies with large bangs and occasional bit of leakage and so on. And there was not a lot known at the time about what was causing this, so I had a look at it, and that's why I started, and it's continued to this day. And I do spend quite a lot of my time working with supply networks, sewer networks, pumps, valves, and so on, and the effect of changes in the network. And we'll see what I mean by that a little later on what that can do. The pressure waves running around through the system. Now, pressure waves, transient phenomena in pipelines, we often refer to this as water hammer. And water hammer is something that we perhaps have all experienced without knowing it. The solenoid valves in our washing machines and dishwashers, for example, which are designed to operate very, very rapidly. Occasionally, a solenoid valve will close and you'll hear a bang in the wall. That's water hammer. That's a pressure wave which is bouncing around in the pipe, consequent to the closure of the valve. If you're really unlucky, you'll see a water stain in the wall. The pipe behind it has burst, and that can be a major issue. Now, we normally think of water hammer as being associated with transient, very high pressures, and these can range from small scale The picture on your screen now is an HDPE pipe, about 400 milliliter diameter, where a water wave simply caused a leak at a joint in the pipe, or they can be large and spectacular. You can see a burst pipe, a burst water main there, with the consequent water spout with the high pressure that's behind it once the initial very high range has gone through. The other picture here is of a 700 millimeter cast pipe, which was totally torn apart by a pressure wave going through it, partly consequent, I should add, not to the pressure wave itself, but also to the condition of the pipe, which, as you can see there, is not very good. But what's often forgotten or not realised is that transient low pressures can be equally as catastrophic. What we're looking at here, these are a couple of irrigation pipelines, and irrigation pipelines are often designed and constructed using non-pressurized pipe on the assumption that because they're lying on the surface or near the surface, the static pressure that they are required to take, the positive pressures, are really quite low. But of course, the operation valve can drop that pressure very, very rapidly, and there are a couple of cases that you see here of irrigation pipes that have been imploded, split through implosion. So causes water hammer. What causes these trends? Well, water hammer occurs in close contact when it's flowing full, and it occurs when there's either a reduction or an increase in the flow with a consequent reduction or increase in the velocity of the flow within the pipe. And let's just illustrate the base phenomenon very simply. Let's just think of a pipeline with a valve that is closed suddenly, and forgive me, but as an aging academic, I can be a bit pedantic about these things. We're going to ignore friction and minor losses. They're irrelevant to the current conversation. Let's say we have a pipe like this, a straight pipe with a valve in the middle of it, an initial velocity right through the pipe of V0, and then very rapidly we slam the valve shut. What happens when we slam the valve shut is that on the upstream side, we still have water entering the pipe at the upstream, but the water adjacent to the valve comes to rest, and is brought progressively to rest as a pressure wave progresses upstream. We would expect that. We would expect that the water that's in here is compressed because you've got water coming in at the upstream end and it's stationary here, and that's what gives rise to this high pressure wave. On the downstream side, the phenomenon is the opposite. Here we have zero flow coming through the valve, whereas downstream we still have flow passing out of the pipe. And so as a consequence of that, we get a negative pressure wave, and the pressure can drop very, very quickly and move downstream. Okay, we'll try and keep this as good as we can. I'm sorry, I should have had that perhaps plugged in a little earlier. Anyway, what you can see there is the very strong negative pressure wave on the downstream side of the valve. And in many ways, because we associate water hammer with positive pressure waves, and we often think that we are dealing with those, I do want to emphasize the fact that these negative pressure waves, as we'll see, can cause very significant problems. Now, the compression and expansion bring the water eventually to rest, and we get these large pressure waves that bounce around the system, positive on the upstream side, negative on the downstream side. These pressure waves travel at the speed of sound. Now, for water in a steel pipe, that's around about 1,200 meters per second. In plastic pipe, it can be down as low as about 350 meters per second to 400 or 500 meters per second. So how significant actually is this delta H we talk about? The equation you're seeing here, I promise, is the only equation in the entire presentation, so try not to be put off by that. It's the Joukowsky equation, which links the transient pressure rise or drop to the speed of sound, which is A is the speed of sound in the water. Delta V is the change in velocity that we're generating by closing slightly or opening slightly a valve or operating a pump, and G is gravity. Now, this equation does help us to determine the maximum water hammer pressure that may occur, but it can't handle the time and space history of water hammer pressures. It can't tell us how to reduce the water hammer by making use of mitigation techniques, and for this we need computer models, and I'll have a little more to say about that a little later on. But let's think of the order of magnitudes we're talking about. If we have a velocity of sound in water of about 1200 meters per second, if we have a change in velocity occurring of about 2 meters per second, say from a velocity of 2 meters per second down to 0, or from 4 meters per second down to 2 meters per second, or whatever, and a gravity of about 9.8 meters per second squared, then delta H is around 250 meters of head. That's a very high pressure head. At the very least, we need to know that something like that is possible within the system I've talked about here, and we need to think about what the implications are. So a very large positive pressure can cause this kind of issue. A very large negative pressure, or even a relatively small negative pressure, as we'll see, can give you this kind of issue here with an implosion. Water hammer can result from any change from steady state flow occurring through a change in boundary conditions. Whether this is changes in valve settings, starting or stopping of pumps or pump trip, number of other ways it can happen, but these are the most common ones. And as I've said, it's normal to think of pipe failure due to water hammer as being due to excessively high pressures, but in fact, there's a mechanism for pipe failure from pressures that are less than the fluid vapor pressure, and that's the phenomenon of column separation. We've seen this little picture before, but you can see that during the passage of this negative pressure wave, the velocity out here is greater than the velocity here, and so this water contained in this area here is being put in tension, being stretched effectively. Common liquids can't stand that, and so you actually reach the vapor pressure of the water very, very quickly. Significant cavities form at very low pressure, and as those cavities move through the system and move into a region of high pressure, then they implode, not explode, they implode. They fall in on each other with the release of a tremendous amount of pressure in the process. And the separation, the column bubble, as it were, then reattaches, it settles down, but with that enormous pressure wave that's associated with it. So I've mentioned that already. Flow reversal will close the cavity. We won't talk about the entire process, but where we get very low pressures forming through column separation, we know we're going to get potentially damaging very high pressures as well. So it's clear from this discussion, firstly, that the computation of the time history is excessively computationally intensive. We're talking about very short time increments as the process is happening. And what we're going to do now is just look at a brief demonstration that highlights some of the issues that can arise in transient analysis. It's just a demonstration. We're not looking at solutions or anything, but just a picture of what might happen. We're going to do this with relation to a very large pumping station. It has 4 large pumps, each of which stands 4.5 meters high and 4 meters across, each of which weighs 45 tons, each of which is capable of pumping up to 8 cubic meters of sewage per second. Now, each pump is fitted with a delivery valve and a suction valve. Under normal operating conditions, the suction valve remains permanently open, and shutdown and startup are controlled by a single delivery valve, which is located on the discharge side of the pump itself. So what we're looking at here is a schematic of the system. There is a large wet well where the pumps draw the water from. Each of them is capable of passing up through one of these delivery lines, through the delivery valves, and the rising main is then quite a long rising main up here, order of 80 meters long, which leads to a delivery chamber. Now, during the commissioning of this particular pump station, with just a single pump running, there was an incident that occurred, and I call it an incident. It was pretty frightening for the people who were there at the time. One pump only was running at 8 meters cubed per second, and it was operating with a valve closure time of 6.2 seconds. The outcome, as the valve closed, there was a colossal shaking of the rising main. There were several loud bangs. The flange joints themselves opened with associated leakage. The pump jumped, and it was all pretty unpleasant. And so the requirement was really to have a look at it, find out what had happened, and then as a consequent to that, looking at retrofitting or changing the protocols of operation in order to remove these transient effects. So I undertook a transient simulation using a model called the Surge engine, which goes with the Pipe 2020 model. This is an analysis model that comes from KY Pipe in the United States. And I might add that consequent to this webinar, we hope to be running a web-based course, and registrants in that course will have access to the model. During the time of the course, we'll be able to operate it, undertake a case study, and also investigate various mitigation measures that can be used. In the current case, we first verified the model against field data by generating a fairly gentle transient. We didn't want to wreck the joint, so we just put a gentle transient through it and instrumented the pipes and the pumps to monitor the pressures and the flows. And that verification process produced a number of comparisons, one of which we see here at the top of the rising main. The small inset there is the data that was picked up from the system itself during that controlled transient, and this is the predicted transient here, and you can see they're virtually identical. So we were quite happy about that. This sort of process is very good when you can do it, because it does give you confidence in the subsequent predictions and studies that you carried out. Now I'm putting this one in to make a point. This is the steady state operation of the pump immediately prior to the incident. The blue line is the pipe itself over a distance of 180 meters from the wet well at the upstream end to the discharge point, the discharge chamber at the downstream end. The pump is located here and the valve just here. The red line is the hydraulic grade line. Very little resistance in the lines, so these lines here are virtually horizontal. But and then the climb, of course, the energy that's added to the system across the pump itself. The important point to note here is the relatively very low static pressure in the long length of rising main here. We're looking at 60 meters there, and in fact this line should be vertical, and so there are around about 100 meters of pipe within which the steady state static pressure is only 3 or maybe 4 or up to 5 meters. And so it doesn't take much of a negative pressure wave to drop it to absolute zero within that line. So the transient simulation of the incident involved running the model with the valve closing linearly in 6.2 seconds with the pump running throughout. And I'm going to do a little bit of a trick now. I'm going to change my screen view here, and I'm going to bring this picture up. Now I've got the simulation model running in the background, and I didn't want to take the time just to switch to that fully and run the model right through to see different aspects of it. We can do that later on if there's time for that. But the screen grab that you see here is actually after a time of 11.18 seconds. Now the way this simulation was run, it was run in steady state first for 5 seconds just to settle everything down. So at 11.2 seconds, the valve just associated with this pump would have been completely closed. So this is very close to the point where the valve is completely closed. And you can see that the whole of the rising main, which is this section of the pipe here, is cavitating. That's what this pictorial image shows you. But you can also see, and that's a dangerous thing, which we'll again have a bit of a look at. But the important thing to notice here, and I'll flick the play button so the transition plays right through, and you can see how it's changing very rapidly. The green is the hydraulic grade line, and these are the envelope lines here. So you can see, for example, that's run right through, and it's back at the end of the simulation. But you can see that the maximum pressure reached during that particular shutdown emergency, during the incident, was over 300 meters of head. That's a very high pressure. So what we've seen there is that we get a highly transient event throughout that simulation. We get these regions of cavitation occurring. We get these very high pressures occurring as well. So now I'm going to go back to where we were. So this is where we left the presentation. And what actually happened, we had the whole length, virtually the whole length of the rising main and the delivery main. About 96 meters of pipe was subjected to column separation. And this happened because the initial steady state up here was only around 3 meters or less. So it really took very little change in velocity to suck that pressure right down to zero. And this is, well, we saw this earlier, but I've just put this into the presentation to emphasize the point again, that when you get this kind of column separation occurring, and associated with it, you get these very high pressures when these cavities implode, you've really got a highly transient, potentially very dangerous situation. So what this investigation showed us was that the cause of the incident was column separation in the rising main, and the system was especially vulnerable to such problems because of the low positive steady state pressure in the long horizontal delivery main. So the high pressures, but now I want to emphasize the low pressures again. As I said, these are irrigation pipelines. Irrigation pipelines, because they're near the surface, are often designed with non-pressure rated or very low pressure rated pipe because it's considered that the steady state pressures are going to be very low. But of course it's and under steady state, no problem. The problems arise when those lines are operated simply by changing a valve changing a pump, you can get these extremely low negative pressures occurring with the subsequent damage that we've seen. So I'm going to leave it at that for now. That completes what I wanted to say. I've got a couple of other slides there in case there's time to look at those, or we can look at the simulation as well if need be. Let me stop there, come back to you, Trevor.
Well, thanks, Bob. That is a really, you can see you've been doing this for quite some time. I mean, this is fulsome, and a large amount of experience and knowledge goes into this work. But no, there's not a comment or question on the board. You must have answered all their questions. That's what I.
Or as you say, stun them into silence. I kept the maths out, so I wouldn't stun too many people.
No, well done, well done. But there's a lot of people on board, and so if you want to travel through the other slides in your presentation, feel free.
Well, look, there are a couple of points I'd like to make, and one of them is the use of gate valves. Now, these pipes are large. The gate valves are very large, and I just want to talk very briefly about the reaction of gate valves to closure. And what's not often known is that if you close a gate valve linearly, which means you're closing it at a constant rate right across the closure time, then what you in fact get is very little happening for a long time.
Your PowerPoint's not appearing at this point. If you want to.
Okay. Well, what I was saying about gate valves is, and this is one thing we discovered with this particular structure that we've just been talking about. The discharge valves are gate valves, and the thing about a gate valve is that it has an effective valve closure time that's very much faster than what you would expect from a full linear closure time. So it's instructive to have a look at the flow history in the rising main of this pumping station during a linear valve closure of 6.2 seconds. And we're looking at that here. Now, the first 5 seconds are not part of it because that's steady state operation anyway, but the valve started to close after an elapsed time of 5 seconds. And then you can see for the next 5 seconds, which takes you down to almost 90% closed, there's virtually no change in the flow rate. This is a characteristic of gate valves that's well worth keeping in mind, because what happens, all the action happens in the last second or two of closure of the valve. Now, in fact, without going into the full details, the change in operation protocols for these valves that was adopted involves a very rapid initial closure and then very slow over the last part of the closure. And that makes a significant difference. So again, without getting too carried away about it, that's one thing to note about gate valves. And that and many other tips, of course, will be a part of the online course. And this is one of those apocryphal pictures you come across from time to time. This is a large, long irrigation, very large pipe, 1.5 meters or a couple of meters in diameter, got a negative pressure wave through it. It wasn't rated for it, and it sucked it in, and that's what the pipe looked like afterwards. And I think that's an appropriate point to stop with an image like that.
What? That is a stunning picture, Bob. Is that steel? I guess it is with the rivets in it.
Yeah, it is steel.
That's an expensive little shut-off valve. I mean,
yeah, exactly.
That costs somebody a lot of money.
Yeah.
We've got a ton of questions coming through, so why don't we just get stuck into those right now?
You want me to click on Q&A, is that right?
Well, actually, there's a few. I'll just go to the chat line first. Maybe Justin, Charles, Gary. Thanks a lot, Harry, Peter. They're putting them up on the Q&A. They were in the chat line. They're coming across the Q&A now. Well, let's kick off with Justin's. Hi, I was wanting to know what was the rising main discharge to atmosphere. Does that make a difference?
Okay, the rising main was carrying 8 cubic meters per second. That was the discharge, and that was going right through to the discharge point. Now, when you say, does that make a difference? Oh, discharging to atmosphere, yes, that makes a difference.
Sorry, I want to put that, yeah.
Yeah, if you're discharging to atmosphere, then by definition, the pressure at the outlet is zero. The pressure on the pipe is zero at outlet. So the negative pressure wave is going to be felt even with a relatively small change in velocity upstream. It'll give you that very low pressure very quickly if you're starting with a steady state pressure that's close to zero.
Great. Yep. Harry has asked, was the 300 meter transient due to the flow reversal?
Yep, that's exactly right. And what happened there is that when all the water comes to rest, it starts to run backwards through the pump. A check valve closes very, very quickly to protect the pump from reverse flow. And when that happens, you get that very high spike in pressure.
Yep. Charles in Queensland has asked, could we have a quick run through the parameters that impact on the surge pressure amplitude? Was that too much?
Okay, the surge pressure amplitude, well, the principal ones, I'm just going to, the wave speed is a critical one. So, because if you think of that, I could go back to that slide perhaps, just, oh no, I'll leave it down. It's that simple Joukowsky equation. The speed of sound in water is a critical one. The higher that is, then the higher is the pressure wave that you'll get, the value of the pressure wave. So in steel, although steel's good and strong and should stand the high pressures, you get the higher wave amplitude itself. So the actual pressure wave has a much higher amplitude in a steel pipe than in a corresponding plastic pipe. That's what, and also the speed of sound is governed by the fixation of the pipe, whether it's free to expand or contract at its ends, whether it's fixed in place. These tend to be more secondary effects, but they are there. So the main things that affect the magnitude of the pressure wave are the speed of sound in water and the rate at which you change the velocity.
Yep.
And one of the things that I haven't talked about is the difference between a rapid valve closure and a slow valve closure. And that's to do with, if you can imagine a wave moving away, or excuse me, if you can imagine a wave moving away from the valve, it reaches a reflection point and turns around and comes back. So a negative pressure wave will come back as a positive wave. A positive pressure wave will come back as a negative wave just because of the reflection process. And a rapid valve closure is where the time of travel of the wave to the point of reflection and back again is less than 2L upon, is greater than 2L upon A. So in other words, I'm sorry, I don't want to get too, it's a rapid valve closure if the valve closes fully before the wave gets back to the valve. It's a slow valve closure if the valve is still partly open when that high pressure wave comes back. And that's the basis for saying that the rate of change of the velocity or the flow in the pipe, whichever way you look at it, can have a significant bearing on the magnitude, on the amplitude of the pressure wave.
No, that's great. We might have to do shorter answers and do more detail on the course, but because there's so many questions coming through. Peter Addison is from WA, consultant in WA. What could have been done in your example to avoid the incident? For example, analysis or modelling as part of the design process.
That's the answer. Analysis is part of the design process.
Well done.
That's the short answer for once.
No, that's fantastic. Yeah, Gary is in New South Wales. Here we are. Yeah, Sydney Water. Upon column separation, when pressure drops below vapor pressure, Does the phase change between fluid, water, and vapor happen instantaneously, or how quickly does that happen?
It happens very quickly, virtually instantaneously.
Yep.
I like to use the analogy of water boiling in a pot. It's
Yep.
just,
Yep.
you can boil water by increasing its temperature or by reducing its pressure.
Right.
It's that process.
Yep. Another one here from Kumar in Tweed Shire Council. Is it possible to reduce water hammer effects by using anti-hammer air valves at critical locations?
Yes, it is.
Yep. Yep. Nana Keong has asked, what minimum pressure design criteria would you recommend?
It depends on the circumstances. A lot of water authorities don't want negative pressure at all.
Yep.
I mean, absolute zero is minus 10 meters of water. So from a safety point of view, in a hydraulic system, depending on the strength of your pipes, you can go to -3, -4 meters or whatever. The issue that you have then is that air bubbles will come out of solution. It won't vaporize, but dissolved air can come out of solution. And if your consumers start complaining that their water has gone milky, they might think of it as a pollutant, but in fact it's not. It's simply air coming out of solution. But in my experience, a lot of water authorities try to avoid negative pressures altogether for that reason.
Mm-hmm. Yep. Luke's senior hydrogeologist in CPM in Perth has said, what flow rate does this start to impact pipes? Is 20 to 200 litre per second susceptible, or are we only talking very large, plus 1,000 litre per second?
These are flow rates. The flow rate, the higher the flow rate, the higher the velocity, depending on the diameter of the pipe. So very large pipes can handle very large flows because the velocities are small. Very small pipes won't handle large flows as well because the velocities are a lot greater.
Yep, yep. Oh, that's great. Oh, we're starting to hone into some of these questions. Thanks, everybody. They're really, really good questions. Yeah, thanks, Charles. Depends on velocity and rate of change of velocity. Yep, that's good. Harry has asked, in downstream scenario flow reversal, probably no concurrent flow happens, vacuum, vapor and water, but an upstream scenario, probably it's all positive pressure, then concurrent flow direction could dissipate part of the energy. Is that correct? So you see the top question there in the Q&A screen. Bob, if you could click on that.
Yeah, I think that's possible, yep. I'd want to think about that a little bit more, so I might take that as a question.
That's all right. On notice. That's okay. Thanks a lot, though, Harry. It's well thought through. Kumar's said again, if we foresee negative pressure developing in the force main, can we insert a vacuum breaker valve? Will this method increase the duty of the pump and hence need a higher capacity pumps?
Okay, that depends on the type of vacuum breaker valve, and it depends on the resistance across the valve. But certainly, as a general rule, yes, it will increase the required capacity, but it's not the only way that you can deal with negative pressures. So, it's one of the ways, but it's not the only way.
Yep. Another follow-up question from Kumar. Will it be possible to incorporate an anti-surge valve close to the pump location to smooth out the pressure transient?
Now, it depends a little bit what you mean by an anti-surge valve. I mean, a surge anticipation valve is, or an SAV as they're called, surge anticipation valves. They're becoming quite popular, and they work by when you start to change a valve, the surge anticipation valve picks up that you've got a small reduction in pressure on the downstream side, and it will open up so that in such a way that when you get the positive pressure wave coming back along the pipe, it will dissipate that very quickly. So what was that called? An anti-surge valve. It's probably a similar thing, sounds like it, and that's how a surge anticipation valve works. But I would imagine it's I'll make a note of that and I'll check that out.
I'll send you these questions too, Bob. Yeah, that's what Kumar called an anti-surge valve. Yeah, close application. Yeah. Well, we might be taking this as a last question, I think. Thanks everybody for your really thought out questions. Jackson is a senior mechanical engineer in KBR Adelaide. Are there other isolation valves beside gate valves that have a more linear flow reduction upon the valve closure, linear valve closure? You see that question?
Yes, there are, and I don't have the details at the tip of my fingers, but I can certainly provide information on that.
Well, I reckon that's about as much as we're going to do today. You can see, everyone, this has got huge. Bob comes with a huge background of experience and knowledge here, and we highly recommend that you go on our website, Twitter, and Facebook and LinkedIn, and have a look at the details for what is coming up. Give us an idea whether you'd be interested in this a course on this topic. That would be good. We really thank you for participating today, and ask you if you could fill in that feedback, a short survey as you close this window. We'll send you a recording, and you can see on the screen there, there's just so many more things happening. Any closing thoughts, Bob, from your side of it that you'd like to make before we close off for the day?
I mean, I don't want to sound like a salesman here, but certainly one thing I would say is transient analysis is vital. You know, there are a lot of I've been involved in a lot of after the event analyses, and it's much harder to retrofit a pumping system to make it work properly than it is to design it so that it will work properly in the first case. So I would say transient analysis should be an essential consideration for all pump networks and sewage network design. Even gravity, you know, I talked about this fast and slow response and rapid and you know, the actual magnitude of the pressure waves themselves. You can have a gravity line if it's long enough, and you start changing a valve in a gravity line, and you can get very high pressure waves. It doesn't have to be a pump system. So I just think it has to be a consideration. You may decide it's not necessary, but you should at least consider transient analysis with any new pumping system.
Yep. In the health sector, you'd say good health is what you need. There's no substitute for it. Go fixing up the problem later is not the answer. You know, taking pills later is not the answer. Having good health at the front. Yeah. So you're saying good healthy system is a good way to go. Hey, look,
exactly.
This has been fantastic. Really appreciate your time today, Robin, and everyone who joined us today. Thanks very much. Stay tuned for future webinars. We've really enjoyed your questions today and your discussion. Thanks so much for joining us. And once again, thanks to you, Dr. Robert Keller. Thanks very much. See you next time. Okay. Bye for now. Yep.
Thanks, everyone.
Subscribe to this YouTube channel by clicking the subscription button. For future webinars and online short courses, please visit our website at australianwaterschool.com.au.